everyone, welcome back to another video of mine, where today we're going to be solving Leetcode problem 77 titled Combinations. So we're given two integers n and k, and we have to return all the possible combinations of k numbers chosen from the range of 1 to n. And we can return this answer in any order we'd like. It doesn't necessarily have to be sorted or really follow any key serialization pattern or anything. It can be arranged however we'd like. Right, so in example 1, we have an input n to be equal to 4 and k to be equal to the integer value of 2. And essentially what this is saying is that we have to return all possible combinations of k, or two numbers chosen at a time, from the range of 1 to n, or in this case 1 to 4. And hence we'd output nested lists or arrays of 1, 2, 1, 3, 1, 4, 2, 3, 2, 4, 3, 4. And essentially, if you were to follow the formula for combinations, which is probably, I think, n factorial over n factorial times n minus r factorial of n choose r at a time. Correct me if I'm wrong, but I think that's either the formula for permutations or combinations. And so, like I said, this is just 4 choose 2, which is going to be equal to 6 total different combinations. And note that combinations are unordered. So, for example, 1, 2, and 2, 1 are considered to be the same combination. And so what that really means is that you may be confused of, hey, we have 1, 2, so why don't we have 2, 1? Why don't we directly start from 2, 3 and 2, 4? Why don't we do 2, 2 and 2, 1? And the reason why is the main difference between permutations and combinations is that in permutations, the order actually does matter, meaning the way you actually arrange the different elements actually does matter and count as unique permutations with different arrangements of the same letters. Whereas in combinations, the order does not matter. So even if you have the same elements for two different groups, they're still going to be considered the same combination if they have the same frequency and number of letters for their groups. So let's say we have perm 1 and perm 2, which stands for permutations 1 and permutations 2. And let's just say permutations 1 is going to be equal to 1, 2, and 3, and permutations 2 would be equal to 1, 3, and 2. Let me just make this a list. Okay, so these are actually considered to be different permutations because although we have the same elements with the same frequencies in both groupings, since they actually are arranged or appear in a different order, right, in this case 3 comes before the 2, permutation 2, these would be considered different permutations because they have, again, different orders of these same elements. Now, let's just say we have combination 1 and combination 2, and let's just say that these are equal to the lists of, again, 1, 2, 3. Let's just use the same example in this case, just for combinations, and 1, 3, 2. Although these do have different arrangements of course, the same letters, or numbers in this case, this should be considered the same combination because we have the same number of occurrences for the same number of integers or elements for both of these groupings, and hence they are considered to be one combination. Hence, that's why 1, 2, in example 1, would be equal to the same combination as 2, 1. So since we already had 1, 2 in the first iteration of our backtracking algorithm, hint, hint, in this output, we would only output 1, 2 and not 2, 1. And that's why that's considered to be only one combination. Let me just delete all that. Okay, so for example 2, we have n to be 1 and k to be 1 as well, and so we only have a range of one element, with only one element being chosen at a time, and so we only really would have a output of just one array with length 1, which of course is the element itself, which is 1, and so since there's only 1 choose 1 for the formula for combinations, we'd have one total combination as we outputted here within this nested array. Okay, so I will give you guys a few seconds to kind of just go over this problem in your head and think of a valid solution, and then I'll tell you guys how I would optimally solve this problem. Okay, so you may have picked it up a few seconds ago in this video, but I actually gave a hint as to which algorithm we would be using for this problem, and that is actually the backtracking or recursive calling algorithm, right? Where we basically recursively call an algorithm until we meet a specific base case, and so we can ultimately append a final list of array, which we can append different combinations to, which we will ultimately return. And so the way we're going to do that is we're going to initialize two variables of final and so far, and these are both going to be initialized to be empty arrays or lists, however you'd like to interpret it. And the purpose of these two variables or data structures is essentially the so far variable is going to be the building up of one current combination that we're building up in one specific iteration of our function, whereas the final array is basically going to contain all the different possible combinations that we build up and add eventually to our final array once we actually meet the base case. And then eventually we're going to be returning our final array once we actually append it or build it up with all the different so far possibilities or all the different combinations that we can possibly have from the different combinations of k numbers chosen from the range of 1 to n, or basically from our parameters of integer values k and n. So now that we've actually defined our two data structures or arrays to actually store these current and final combinations, now let's actually define our backtracking function to actually start our recursive algorithm. So I'm literally just going to define a backtracking function here. You can call it whatever you'd like, but just for the simplicity and readability of this code, I'm going to call it backtrack. And for any parameters, I'm just going to pass in one parameter to be a start. And this start is basically going to be the starting index for every iteration as we loop through all the different values from the range of I to n for k different combinations of numbers. And that's how we're going to basically serialize and choose which numbers to actually choose from in one specific range or iteration of this function. Once I do that, I'm going to have to basically, for good best practice, like I always do in all my backtracking functions, you should always have your base case appear first in the backtracking function. And in this case, our base case is essentially going to be, do we have k numbers in one specific combination that we're building up? If we have chosen completely k numbers in this combination, great, we have found another unique valid combination that has or meets the criteria of using k numbers and exactly k numbers. We would simply add that so far combination that we're building up in the current process to our final array, which we will ultimately return after we do this process until we process and parse through the entire input. So if a base case in this case is going to be if the length of the so far array, or in this case if the length of the so far array, or in this case basically our current combination, if that's equal to k, basically meaning that we've used k numbers in this current combination, then we can final.append or add to our final list of combinations a copy of the so far variable. And the reason why we actually do a copy is because we're actually going to be changing this so far combination based on the different numbers that we actually use in our valid range. And so we actually should have a copy so we get that correct process or element in this specific movement or iteration of our current combination. So we don't actually change the value and mess up what we're adding to our final array. Once we actually do that, we'll actually just use the return keyword to basically stop the execution of this function and move on to the next call or execution of this function, because we're done, we've hit the base case, we found another valid combination, and we don't want to keep executing this same block of code. We want to move on to the next iteration or the next execution for the next valid combination of our input n and k. So that's why we do return. After that, this is where we actually start our recursive call of this function and actually have this recursion in our code. So the way I'm going to actually set this up is just using a for loop to actually iterate over the values from my starting index until that nth value. And I'm going to do this like so. So I'll say for I in the range of essentially my starting index that I pass in a parameter and basically n, right? But in this case, in Python and most for loops for most main programming languages, the second parameter that we actually pass, or basically our boundary point for this for loop, is actually going to be exclusive. And so if I want to include n in this for loop, I'd actually have to do n plus 1, because then this would be considered as n plus 1 exclusive, or basically all the numbers from the range of the starting index or starting value up until the nth value inclusive. So once I actually do that, I want to simply add to my so far combination, so far.append, my ith value, or basically the iterator that goes through all the different values from that starting index until that nth value. And now I have to basically recursively call this backtracking function, but instead of my parameter just being start, because that would never be updated, I'll actually have to pass I plus 1 to move on to the next element, right? To basically move on to the next iterator or element to add to my current combination. And once I do that, to explore all the different further values in my range of 1 to n, I have to do so far.pop, or basically pop the most recent value that I've added in my current combination. And this basically cleans up or undoes what we've done so far in the code on lines 11 and 12. And this enables us to explore all the different paths or different combinations from one number to the rest of the numbers. So basically, instead of just following a linear path of 1, 2, 1, 3, we can actually, or 1, 2, 1, 1, 2, 3, 3, 4, we could actually go in a nonlinear path and actually explore all the different paths or nodes, in this case if we're thinking of it as a tree, to actually explore all the different valid combinations within this range, to actually skip over numbers that we've already used and move on to different combinations. So for example, to better visualize this, if I had maybe per se a list of 1, 2, that's already in my final array of different combinations. And so I don't want to use this again. So I'll pop from my list, or basically my current combination, and instead of adding the second element, or element 2, because I already had that combination, I'm going to call backtrack at I plus 1, move on to the next element, and add 3. Great, I've used this combination. I'm going to pop again, call backtrack at I plus 1, move on to the element 4, or the next element from 3, which is going to be 4 in this case. Now I have 1, 4. Great, once I've done that, I can pop again. I've already used 1, I'll pop again, and I'll backtrack at I plus 1, because basically my range is done. I've looped through the range of start to end, and so now what I'm going to do is I'm going to basically restart from fresh. I'm going to start from an empty list again. Now I'm going to start with 2, and now I'm going to say I plus 1, so the next element from 2, which is going to be 3. I'll undo that. I'll move on to the next element after 3, which is going to be 4, and so I'll get 2, 4. Pop here, pop again, because I've reached the end of my iteration of for in the range of start till n plus 1. I've already hit my max value n, which in this case is 4. Now we'll start with 3. 3 plus 1, or basically backtrack at I plus 1, is the next element is going to yield 4. Great, I've hit 4, which is the last element in my for loop iteration, or the n value, and so I'll pop again. And now I've hit 4, but I can't iterate anymore, and since 4 does not equal the length of k, because we're not using 2 elements in this combination, I'm going to stop this execution and simply return my final array for all those different combinations as we talked about before, for all the previous iterations that we talked about in this recursive call. So once I actually do that, now I'm done with my call, and now I'm done with my backtracking function, and I can simply call backtrack, and for my parameter, of course, I'm going to pass in 1, because the problem statement clearly stated that we have to actually loop through the values from the range of 1 to n, and so I start from value 1 rather than 0. And ultimately, once I'm done calling this function, I will have added all these different combinations that actually build up with my so far variable into my final variable, and I can simply return final once I'm done calling this backtracking function. And so unless I made any syntax errors here, or just spell something wrong like I always do, this should be completely fine, and it should be accepted. Looks like it's taking a while to actually judge, but as you can see, it's just about as efficient as you can get. Of course, runtime complexity-wise, this is going to be O of n choose k times k, because this is a combination problem, and it really just depends on our n and k variables of how many times we actually choose from a pool of n numbers, k times, where n and k are those two parameters. And of course, memory-wise, as you guys can see, this is going to be of the same thing, because we're actually using 2 extra data structures of final and so far to actually store those n choose k, or basically choose k different times at one iteration of the pool of n total numbers, and that's why that's going to be n choose k times k. So if you guys enjoyed this solution and understood this backtracking algorithm, please consider liking this content and subscribing to my channel. It really does mean a lot, and without further ado, I will see you guys in the next video. Bye-bye.